Team lost. That's the way it goes, though. That's the way it goes. Bears lose. Here we go. All right. Our questions. What is the domain?
The x-intercept.
Not the intercept. Great. X's. All the possible x's of a function. So any x value that yields some sort of output, right? Good? We have trouble? Okay. Oh, God. I was going to yell at a kid. I was about to yell at a student. Go away. All I need is nonsense. Anyway, sorry. So what's the range?
Y.
Any of those y's, all those y's that come out. Now, do you remember, this is the hardest part, right? Do you remember how to list the domain? You don't.
Open thing like this.
Oh, okay, okay.
X.
So you're talking, yeah, let's go. X
One.
such that
X.
all x's,
Whatever the domain.
it's all of them, right?
Yeah. So
All of them. So we could just leave it as x, and it's an element of
real.
reals. Wow, you guys are so on top of it.
I guess that. I didn't wonder.
Well, it was a great guess, right? It's an educated guess.
I wrote something. He had no basis on that guess.
And so I'll just label it as D for domain. Great. Good. No reason. Close it up. The range.
All Y's.
Is it? Are there any Y's down here?
No.
Underneath? There aren't. Do you know why?
Because it's going up.
It does go up. Do you know why it goes up in a V like that? Do you know what these little lines symbolize?
No.
No? Anybody ever heard of it? No negatives. Do you know why? Do you know what it's called?
No.
Oh, well.
Absolute value.
Yeah! See, I knew it.
Oh, I thought that was
Absolute value. So we know all the y's such that y has to be greater than or equal to what? 0. And then they are all reals, just like the other. Right? Woo! All right. I'll let you catch up. I would rather you wrote this down before we started, because this is just me checking in to see if you remember.
I remembered that. I remember.
Great. Good. Got it all written? We're good? Okay. Now, what are we doing? What are we doing when we're talking about the domain of a function, the range of a function? We're going to talk about continuity of a function and behavior of a function. What are we doing? We're looking at it. What do we call that? Do you know?
Continuity.
Well, continuity is part of it, right? We want to see if a function is continuous at a specific point, right? That's good. Yeah? Water is good for you. All right, so what we're doing is we're analyzing, right? We're looking at a function and we're telling ourselves, hey, I know a specific amount of information just by looking at a function. I can see, hey, this points up, right? So if both sides are positive and it's just a simple absolute value function, it would have been a straight line if those absolute values weren't there, right? Yeah? Good? All right. You ready for the new stuff?
Go ahead.
Let's go.
This is a tough one, man. And only because of the language. You're not used to language. So I am on page 16.
Yeah. Go.
Right? And on page 16, it says continuity and behavior and limits. These are all calculus ideas. You are learning the very beginnings of calculus, or sometimes what we call the middle of calculus when we're just talking about derivatives. But it says continuity. A function is continuous at a specific point on the x-axis if it satisfies the following conditions, right? So one, it has to be defined. The output is defined at C. In other words, if you put in that number that we give you for C, you get out a real number. Okay, so if I have a function, is this function, let's make it nice and simple. Is this function continuous if I'm talking about, if we say that x equals 2, well, if I put in a 2 for x, do I get out a real number?
Yes.
I do. Because f of 2 is basically 2 plus 1, which is 3. 3 is real, so we've satisfied letter A. What does letter B say?
We see letter B.
fx equals 2x.
Oh, sorry, 2. I call them A, B, and C. Number 2, f of x approaches the same function value to the left and to the right of C. In other words, a limit exists. Well, you guys don't even know what a limit is, right? So let's talk about limits. I'm not going to go into major, super specific, in-depth ideas of a limit, but a limit is where the function is headed, what y value is coming out at a specific point. Okay? Ooh. And so let's use an easy one. Oh, God. I'm writing off the screen for some unknown reason. There we go. So let's create a function, a nice simple parabola.
Bless you.
God bless you.
Bless you.
F of x equals x minus 2. X squared minus 2. Right? And we're going to say, is this continuous or does it have a limit at x equals 0? Right? If I put in a 0, I get out what? I get out a 2, right? Because 0 squared is still 0 plus 2 is 2. So here it is, down here, 0, 2. Sorry, it should be up here. Oh, no, I was right. Negative. Minus. I did write it right. I said it wrong, but we're there. Good? All right, 0, negative 2. So if I put in a 0, I get out a negative 2. So the first condition is met. Now we have to talk about it. Is this
That's a negative 2, 0,
0, negative 2? Yeah. So if we sweep from left to right along the x-axis, but we're following the goes, right? Are we getting to the same point from the left side and the right side? Do we approach this center point at the same y value? Does it come to the same y value from both sides?
Yes.
It does. This is probably the most annoying part of learning limits. Yes,
This is off topic, but did you set the alarm?
I did not. I'll pull it up in a minute. So, for this function, if we're looking to see if it's continuous at 0, we get yes, number 1, yes, f of 0 is equal to -2, and 2, the limit is also equal to -2 because that's the y value we're approaching from both sides. We're coming at it from both sides and we're approaching -2. So when we look for a limit, we're looking at a y value or an output value that is the same from both sides. Number 3 says the function value that f of x approaches from each side of C is that output value that we had in number 1. So if we have a limit and the limit value is the same as that output value, so if it exists and it has a limit and that limit is the same as our original real number output for number 1, then we have a continuous function. That's a lot. It's a lot to take in. And I don't want you to cry. No tears today. I gotta get to my alarms. There it is. Set. Now, are you sure you're having class at 10 o'clock today?
Sure, Tuesdays it's at 11.
Tuesday she starts late.
Yes.
Okay.
Only Tuesdays.
Only Tuesdays.
Only Tuesdays.
Solo Monday?
Ask him, I don't know. Solo Matade? Monday? What the? I don't know.
Lunes.
Sí.
Lunes. Monday.
Douglas, don't forget
See?
to write it down.
See?
Before I leave.
All right.
Whatever. Nanya.
Wow. There we go. Okay. So let's look. Boring. Let's look at functions. And I'm just going to draw something. Okay?
What the hell? That's what you call that, so on the graph.
This is a piecewise function. Okay? It's 2 pieces. You see down at number 1 at the bottom how it's 2 different things?
Yeah.
See how it's 2 different things? And you have conditions that you have to. We did this a little bit previously when we had to input values, right? And if the value is greater than 2, we use that guy. I almost did this the way this looks, but I didn't. This is quite similar. So this one is a piecewise function, right? F of x. And what I wrote here was, I think, x squared minus 2 plus 2 if x is greater than 2. Okay? That's what that says. This one down here, right? This is just x minus 2 if we have an x value that's less than or equal to 2. Cool? Good? That's what that says. That's what I just created. So go ahead and copy that down in your notes.
Can you write the name of that graph on the board, please? The name of the graph you write on the board.
I think so. I think that's it. It just has two different pieces and conditions. God, it's all in one video. Are we there?
Nope.
I should move that camera back.
First, you want to be like Ceci around.
Get it sexy.
Do you?
Get it sexy.
She get money.
Said she got money.
She get money.
I get my own.
Okay, but she get
Are you done copying?
No.
Talk less. Copy more.
Yes, Mr. Sue. I was talking.
Tommy.
Hmm?
Tommy.
Doesn't matter what you were doing.
Yeah.
I needed to get done.
Racing your playlist, bro.
Come on, come on. You haven't written a single thing down, Mr. Calix.
Because I've been taking mental notes.
Okay. Since Calix isn't writing anything down, we'll have a little quiz on the show.
Chill. You better get on that.
See, bro, why is it all?
It's always you.
Oh.
I would love a quiz, Mr. Sue.
Bro.
Poor Calix.
Get on the pencil and paper, bro.
I'm taking mental notes.
No, get on a fucking pencil and sorry
Okay.
to curse it. Get on a pencil and paper.
Bro, if you
Bro,
don't
get on a
understand-
pencil
bro,
and paper, bro. I'm not
He's
trying
sorry
to
about the
quiz,
language.
bro. Why would I have to work to keep my easy 100 if I can just keep it, bro? But get on a pencil and paper.
I'm keeping
Bro,
it.
get on a pencil and paper, bro.
Hey,
Bro, you're making
Sean,
he's making my life harder with this.
You'll be
math.
good. You'll be good. I will not punish you.
See, you're not gonna get.
I'll just quiz him. How's that?
Yes.
Good? Or, how about this? How about I give you the exact same thing as a quiz and let you use your notes?
Yes.
Let's do it.
I'm not there, Mr. Sue.
Right?
You should do that.
All right, we good? All right, so what it says here is if my x value is greater than 2, I'm going to use this part of the function. If my x value is less than or equal to 2, this is the part of the function I use. So if I wanted to find a y value for -1, I would use this bottom part and put in a -1 for x minus 2. So -1, -3 would be right there. Does that make sense? So that's if you want to find a value.
Yeah.
If I want to find continuity, if I want to know if this function is continuous at x equals 2, continuous, that's the hardest word for me to write in math for some reason. All those U's and O's and U's. Continuous at x equals 2? I don't know, let's find out. So now, we don't even have to do any math. All we have to do is look at the graphs themselves and see, if I put in a 2, do I get something out? Yeah, there's a closed circle here. So if I put in 2, I get out 0. So number 1, yes. Because f of 2 is 0, right? So there is a value that comes out. Here's my problem. If I look at this graph, are we approaching the same value from the left and from the right. Looks like we're approaching an output of 0 here, but an output of 2 here.
Yeah.
We're getting infinitely close. When we talk about limits, we're using calculus to get as close as possible to an output value because there's no real value right here. That's why the open circle is there. Remember open and closed circles from inequalities?
Something like that.
Oh.
Right? So there's no value there. This value doesn't exist in 2 places. It only exists in 1 place. This is open. But as we follow the graph, we're getting really, really, really close to an output of 2, but never quite getting there. So no, we don't approach the same value from the left and the right, so no limit. So because of number 2, we're discontinuous at x equals 2. And I'm going to explain to you what kind of discontinuity this is. There are 3 types, right? It says there's infinite discontinuity, jump discontinuity, and removable discontinuity. Now, watch what happens as I go along this graph, and you can tell me what type of discontinuity it is. We go up here, and then we whoop, and then move along. What kind of discontinuity do you think that is? Watch. Whoop.
A skip.
A jump. How easy is that? So at the same spot that you're looking at, we jump from here to here.
I'm out of breath.
That's a jump discontinuity.
That's not how it
Okay,
Do you want to see what a removable discontinuity looks like?
Yes.
Super duper easy. Ready?
goes.
Here's removable. It would be a completely straight line, except right there, it doesn't exist.
Okay. And it's the only thing is jump and removable? That's the only thing.
Removable. The most annoying one,
Oh, so it's 3.
infinite. It's on your sheet. You have a highlighter?
Yeah.
You guys have highlighters?
Yeah.
No.
I would, sure. Are you sure? Are you sure you don't have a highlighter? All right.
So, sir, that means number 2 on page 17 is a infinite.
So we need to highlight something.
You see it.
No, I don't.
The bottom right, right?
Yeah.
Yes. All right, so here's infinite. And I won't act like an idiot like I usually do. So infinite discontinuity means, sorry, that's right. It never touches that y value or that x value, depending on what the function is. Cool? This is infinite. And these empty spaces here, their own special name. Asymptotes. Asymptotes.
I heard of that.
Right?
I've seen it.
Is there a reason for that?
And an asymptote is a line, a part of the graph of the function that the graph never touches. So say this is the x-axis. This function never gets to 0. It gets infinitely close to 0, but never gets there, right? Well, say this is -1 along the x-axis. It gets infinitely close to -1, but never actually gets there. You can put in any old number that gets super, super, super close. It's not going to get there. Okay, and you're going to see in certain functions, not these at the bottom of the page, but the ones on the practice page, you'll see infinite discontinuity when you have higher degree functions that are division, and that denominator is 0. Okay? Because that doesn't work. But I want you to go ahead, we're going to take a look at both of these exercises at the bottom of the page, and we're going to make a determination. Yes?
We need to highlight something.
Yeah, I would highlight on that sheet the infinite, removable, and jump discontinuity words there. And it'd be really cool if you highlighted it in your notebook, because then you sort of have that visual that goes along with it. So, I think it's still 2, right? Greater than 2x plus 1.
Google?
And then x minus 1. All right. So here's our graph, and I'll graph it real fast for you. So we're going to do the tests. Are you scared?
Wait, oh, God, man.
Oh man, I'm sorry.
It's cool, it's cool, it's cool.
I
So
apologize.
the chair, Tom?
You okay?
It's strong.
X minus 1. This is number 1 at the
Yeah,
bottom
sure.
of your study guide intervention page.
On page 16?
Yeah.
That's what I thought. And you doing it.
I do. I hope that.
No, the squad leaders, dashing the squad leaders.
And exos.
And it hurts, you got shade.
Why did I see? Because you got to see.
Because you got face on your face. I mean, I say face on your face. Hair on your face.
2x
Where?
plus 1.
You touching it. There's something going, they gotta go.
Where?
When you pull it,
No, why here?
see, you know where there. You got a shade.
She's talking about this. That's just a shade that it's just going back.
Okay, here we go. There's the graph of the function. Get a little straighter view on that. Is this function continuous at x equals 2?
No. Wait.
This
Yes, but it has no limit.
Really?
Oh, that's not the same one.
If it doesn't have a limit, can it be continuous?
No, it's
No.
It's discontinuous, right?
Yeah.
So this is what you see in number 1. I've graphed it here for you. So you can see that we have a jump, right? Because if you, even to find the limit, all you'd have to do is put in a 2 here and a 2 here. Do you get out the same number? If you put a 2 up here, you get out a 5. If you put a 2 in here, you get out a 1. So you don't get the same number, right? Did I write it wrong?
No. I'll try. I'm lost. You're good. I'm not.
Right?
I'm up to speed.
Cool. So does it satisfy the first requirement? If we put in a 2 here, do we get out a real number? Yeah, you betcha. Yeah. Yes, because f of 2 equals 1. Right? But are we approaching the same value from the left and the right? No. It skips up here, right? So 2, no limit. Different y's from left and right. So 3, nope. And it's a jump. Discontinuity. Woo! Oh, I don't want to move on to that. We're getting late. Because you guys are going to be going at 3 then.
Okay,
2 minutes. 2 minutes. And then we hand out your homework.
You said what?
He said homework.
I said, let me hand out your homework. On your homework, I'm going to go through one of these, or 2 of these maybe,
We're all good.
and it'll be on the video. Because we're just going to input values to figure out whether it's continuous at that point. Okay?
Did you write it down, Douglas?
Huh?
Did you write it down?
So your homework is numbers 1, 2, 3, and 4 on this practice page that I'm handing out. 1 through 4. 1, 2, 3, and 4. We're going to do 1 and 2. 1. I might do. Maybe I'll do. I'll definitely do number 1 in class. That you boys need to go.
You said it. What did they say?
1, 2, 3, and 4.
1, 2, 3, 4. It will be posted.
Yo, stop sleep fighting.
Enough. You guys play any more? I'll just start handing out detention.
Don't go over this.
Yes, you.
They used to date each other.
That was a long time ago.
All right, can you guys move along so I can get through with this?
Thomas,
Yo,
you remember when you did it early?
you're good.
Huh?
You're good.
Stop.
So they actually have history though.
What you're saying means nothing.
One through 4.
Be nice to each other. 1 through 4. All right.
What? What you mean when I get the money? What you mean when I get the money? You don't have the money?
Yo,
Did you just rip up my deal?
Figure ripped up his contract.
I'm still a plea.
I'm not waiting until you graduate for my $20. Cause I'm probably gonna forget.
What did you get on?
None ya.
Business.
Mind your business. Okay, stop being nosy.
That is my business.
And
What?
he's mine too, and I'm telling you to mind yours.
Come on, get out, get out. Couldn't be so.
Have a good rest of your day, President.
Here we go, here's number one. Here's the easiest way to solve these, to find continuity. Step one. We're trying to find out if this function here is continuous at -1. So step one, input. Input -1 for x in the function. All right? So f of -1 is equal to -2 over 3 times -1 squared, which is -2/3. Is -2/3 a real number?
No.
Is -2/3 a real number?
Yes.
Yeah. Yeah, absolutely. It's a fraction, it's rational, so it's part of the reals, right? Great. So, for one, for condition one, yes, -2/3 exists. Step two. This is the more difficult step, but I'm going to try and make it a little easier. You have a calculator in front of you? So, actually, you'll have your computers in barracks to do this, right?
Absolutely, sir.
All right, so open up your computers and go to Desmos. So graph it. Step two, graph it.
So am I inputting the base problem?
Yeah, you're inputting this function right here. And when you graph it, you have a little fatty, a little bit of a wide parabola, basically. But it's got a little hole in it. But that hole isn't at -1, that hole is at 0. We're looking here. Do we get it? You know how to do it? Little keypad, lower left. Do A over B, well, you do the negative and then you do A over B. Yeah,
Honestly,
no, don't put the x equals 1 in there. Take that out. There you go. Oh, that's goofy looking. Huh. Shows what I know. Okie dokie. We have, let me put it in my calculator, see if I can get it right. Yeah. I don't know why yours goes up there, but we should have some sort of infinite discontinuity here at 0. But I'm looking at -1. I want you to look here. Look up here for a second. You see where -1 is on Desmos? Is it continuous here? Does it go straight through there without a hole or anything? At -1 along the x-axis, is it continuous? At that one spot. It is continuous at that one spot. If I had said 0, you'd say no, not a chance. It doesn't exist there. It's an infinite discontinuity. But looking at the graph, it does approach the same thing from the left and the right. Now, if you wanted to go ahead and you see that 2/3 exists, right? When you input the -1. If you put in -0.99 into a calculator, you would get out an answer. And if you put in -1.001, you would get out an answer. And you would see that it's continuous. But just by looking at the graph at that one spot, you'll see that it's continuous. And you'll know that it does have a limit. It approaches, so 2, condition 2, sorry, wrong color. So condition 2, yes. The limit is equal to -2/3. So that means that 3, if it exists, and the limit and the value you get out are the same, then yes, it's continuous. But you could have cheated, because when you graph it, you can see that it's continuous at that point. Good? All right. A lot of things can be done just by inputting the value, seeing if it exists. And graph.